All right, folks, in this video here, we're going to talk about page 167a. Before we talk about this question, I actually do want to go through some of the basic remainder theorem rules with you guys, so then you understand what remainder theorem really is. Okay, so let's take a look at the notation first, right? So the introductory to remainder theorem, Px is used to represent a polynomial expression in terms of x. Dividing this polynomial by different terms gives Qx, the quotient. Substituting a value of x, such as x equal to 2 into Px is indicated by notation P2. So what does that mean is if we look at some division that we did, like as simple numbers. For example, if we use 7 divided by 2, and this is equal to 3, remainder 1, right? So a couple names. This is called our divisor. This is called our quotient, and this is called our remainder. So this whole theorem is based on the remainder theorem over here. So taking a look at exercise 1, 2, and 3 on page 163, we know that if, right, apply the remainder theorem to find the remainder when the given Px is divided by terms on the right. So basically this is going to be divided by that. All right, so how do I find what the remainder is? If you know that x to the power of 3 minus 7x squared plus 4x minus 3 can be divided by x minus 2. And you will be getting a quotient. In this case, according to what we learned over here, right? We're going to be Qx. So let's write down Qx over here. We don't know what it is, but definitely you guys will be able to find it out if you use the dividing polynomial method, right? And plus a number. And this number is our quotient. Oh, let's erase that. Our quotient. Oh, remainder, my bad. So remainder. Okay, so in this case, how do I know what the remainder is? Simply, we just have to find out, okay, what number makes x minus 2 in this case, right? 0. And x equal to 2. In this case, x equal to negative 3. In this case, x equal to 8 plus 1. And in this case, x equal to 1 over 2. In this case, x equal to negative 2. So these are the numbers that actually make this simple divisor 0. And all we need to do is we substitute this value, in this case is 2, into the original function. So the remainder theorem says if you do that, your answer is going to be your remainder. So you'll be able to find out what this remainder is. So it always works. Okay, so with that being said, let's go back to page 167, right? 167a. So one thing that I also want to mention too is one thing that I want to mention too is that there is something that the textbook actually didn't explain. It's called the degree rule in polynomial division. So what does the degree rule mean? Technically is something over here. Remember that when the divisor is a third degree expression, the remainder is expressed as a second degree expression. And you might wonder why. Like, why is it like that? This is actually very strict following the degree rule. So for example, in this case, your divisor is x plus 1, x plus 2, x plus 3. But then what if you have x plus 1, x plus 2, x plus 3, and also x plus 4? So instead of ax squared plus bx plus c, you will actually be dealing with ax to the power of 3 plus bx squared plus cx plus d. So this will be the remainder that you're dealing with, right? So your remainder is always 1 degree lower than your divisor. So when you divide one polynomial by another, the remainder must always have a lower degree than the divisor. Doesn't matter how. So with that being said, if we look at this question one more time, so we know that when a polynomial p of x is divided by x plus 1, x plus 2, x plus 3, definitely we're not dividing them individually. We're actually dividing them as a whole, which means that x plus 1 plus times x plus 2 times x plus 3, which is this. And it says that the remainder is 2, 3, 6 respectively. We're going to talk about these ones later. Remember, these numbers over here, what we did before is that we find out what number makes this 0, and -1, -2, -3. So my assumption is that if I substitute -1 into px, I will probably get 2 as my remainder. If I substitute -2 into px, p of x, I will get the remainder as 3, and so on and so forth. So I substitute -3 into the p of x, I will get 6 as my remainder. So now, with that knowledge, I'm now able to construct this whole equation. So my equation, right, if my quotient is q of x, then I will let my remainder to be ax squared plus bx plus c. The reason we will talk about based on the degree rule in polynomial form, because we're dividing a x to the power of 3, right? Because you have x plus 1, x plus 2, x plus 3. When you combine them, multiply them together, it's going to be x to the power of 3. So your remainder has to be 1 degree or has to be a degree lower than that, okay? So now, this is how the polynomial can be expressed. You will have your divisor here, you have your quotient, and plus the remainder. This is like 7 is basically equal to 2 times 3 plus 1. This is your divisor, and this is your quotient, this is your remainder, right? So this is the structure of that. So according to that, I will know if I substitute p equal to -1 into this whole function over here, what will happen is that my remainder, which in this case is just ax squared plus bx plus c, you just have to simply substitute the -1, -2, -3 into this function, which is a quadratic function that you're dealing with, and you get these 3 equation over here. And guess what? You can use simultaneous linear equation to solve for that, right? How do you solve for that? First, you use 3 minus the 1, right? Now you only have A, B, C, A, B, and C. And your job is just to find out what A, B, C is. If you find that out, you can use number 3 minus number 1, getting rid of the C. That's why you get the 8A minus 2B. And then from 2 minus 1, you use 2 minus 1. You'll be able to get rid of C again. Then you have another function with A and B. Then therefore, you'll be having 8A minus 2B equal to 4. And then 3a minus b equal to 1. And then you can solve for a and b respectively. So when you substitute these numbers in, you'll be able to get the remainder is equal to x squared plus 2x plus 3. Okay, so that being said, I do want to also talk about 168. So a lot of our students are struggling with this question because they see this is x to the power of 10 is such a big number. But then again, if you're divided by x squared minus 1, guess what? Your remainder is just going to be 1 degree lower, which is, in this case, ax plus b. So that's the 1 degree. And if you wanted to talk about the second degree, that's that. And third degree is 3, 2 plus cx plus d, so on and so forth, right? So in this case, since our divisor is just x squared minus 1, we're just doing 1 degree lower. Okay, so now, my quotient, just like the formal question, my quotient, my divisor, this is my divisor, this is my quotient, and this is my remainder, pretty simply put. And then if I put, when I have x is equal to -1 or x is equal to 1, I substitute this into this guy over here, right? So it's pretty simple because 1 to the power of 10 minus 3 is going to be -2. Another one, -1 to the power of 10 minus 3 is going to be -2 as well. So corresponding to different answers, you have a plus b and you have -a plus b. So if you plus them together, you have 2b, which in this case is going to be equal to -4, just like that. And you get b is equal to -1. And you substitute b back into equation number 1, and you'll be able to get 8. So with that being said, if you ax plus b, all right, you already have a, which is 0, and you have the b, which is -2. The remainder is just -2. So not really hard, as you can see that even though the targeted polynomials is such a big number, looking at x to the power of 10 minus 3. But if you know the rule of polynomial, like the rules of that we talk about, the degree rule in polynomial division, you have no problem understanding that our remainder is just 1 degree lower. Okay, hopefully this video helped you guys understand the remainder theorem. If any question, please leave a comment or ask me in class. Thank you.